Okay, so in this video, we're going to talk about tangent planes and linearizations for functions of two variables. Um, and so those terms might sound familiar from first quarter calculus, where we did tangent lines, and we also did something called linearization. So it's very similar. So quick review from 17a, equation of a tangent line to a function at a certain point x naught, y naught. Just using this point slope formula, y minus y naught. Normally this is m, right, the slope of your line, but of course the slope would be given by the derivative at your point times x minus x naught. The linearization is also called the tangent line approximation. It's actually the same. These are one and the same. They were presented together in 17a, or when we talk about the linearization, it really is just the same as the tangent line. The only difference is we're going to replace y with L of x to kind of emphasize that it's a linearization. It's a function of x. And instead of using x naught, y naught in 17a, they used x equals a. And so the y value for a would be f of a, which is the equivalent to y naught. We're just moving it over to the other side. And then that's pretty much the same, right? F prime of a times x minus a. And just a quick review of why linearization in particular was kind of an important idea. The whole idea of a linearization is to approximate something. So say we wanted to approximate the square root of 5, and we could do a linearization for the square root function at a equals 4. Why? Because that's a nicer number, right? We know the square root of 4 is 2. So, and then, we got the math here, but more importantly, I want you to see what's happening. Here's the square root function. Our nice value is 4, where we want to approximate our square root function is at 5, right? So when x is 5, whatever this y value is on the curve is actually the actual answer for the square root of 5. But the idea is you would need a calculator to do that. But if we instead plug 5 into our tangent line, which was drawn at 4, you can tell that, okay, this is not drawn to scale, so it looks like a fairly large difference, but in reality, right, this is going to be a pretty minor difference between the two answers, okay? And so when I do my linearization formula, okay, I ultimately end up with the equation of a line, and then what I would do is plug in 5 for x, and that gives me a pretty good approximation for the square root of 5 as 2 1/4. So now let's move to 17C, and we're in 3D. Okay, now we're in 3D. And so the equations just get modified a little bit. Instead of a tangent line, see on a surface, there's lots of tangent lines, but there would only be one tangent plane, right? A plane is like a flat surface that just barely hits our three-dimensional curve at one point. And so our tangent plane at x naught, y naught, z naught, notice it looks very much the same. It starts off the same, z minus z naught instead of y minus y naught. And then with a tangent line, there was only one way to take a derivative in 17a, but now we've talked about two partial derivatives, right? There's your partial with respect to x, evaluated at this point, times x minus x naught, and your partial with respect to y times y minus y naught. The linearization formula, which is, okay, even though we're using the same word linearization, which kind of implies a line, we're using that same thing to be a tangent plane approximation. Okay, it's really a plane that we're finding. But similar to 17a, this and this are really the same formulas. We're just going to replace z with L of x, y. Z naught would just be the value of the function at x naught, y naught, so that's really the same as z naught. And the rest of it is exactly the same. It's identical. Also similar to 17a, let's start with the linearization, because the linearization usually means if they ask for a linearization that they're going to want to approximate something. So let's say I have my function is x cubed y to the 4th. I'm going to do a linearization at the point 2, 1. Okay, because I could easily do 2 cubed and 1 to the 4th. I can figure that out. But ultimately what we want to do is approximate f of 2.20.9, which would be, if I put that in here, 2.2 cubed times 0.9 to the fourth, right? And that would be harder to do without a calculator to figure out what that is. Okay, so my linearization formula involves the partial derivatives. So I did the partial with respect to x. Y is a constant, so it stays there. Derivative of x cubed is 3x squared. I'm going to evaluate that at my point, and I get 12. F sub y, this time x is constant, so that stays there. The derivative of 4y of y to the fourth is 4y cubed. Plugged in at 2, 1 gives me 32. So my linearization formula is f of 2, 1, which, okay, you just plug that in here, right? 2 cubed times 1 to the fourth, that gives me 8. Plus 12 times x minus 2, plus 32 times y minus 1. Then we can approximate f of 2.20.9 by just plugging it into our linearization. And it's better to not distribute, and it's better to leave it like this, as you can tell, because if I put in 2.2 and minus 2, that's just 0.2, and 12 times 0.2 would be 2.4. If I plug in 0.9 for y minus 1, that's negative 0.1 times 32 is minus 3.2. And I can add those together without a calculator fairly easily and get an approximation that 2.2 cubed times 0.9 to the fourth is roughly 7.2. You can check it on a calculator to see how close that is. All right, how about a tangent plane? So my equation is z equals 4x squared minus y squared plus 2y, and I want the tangent plane at negative 1, 2, 4. This would be your x naught, y naught, z naught. You're also going to need your partial derivatives. So f sub x is just 8x. If I evaluate that at negative 1, 2, really I just need the negative 1. That gives me negative 8. F sub y is negative 2y plus 2. Once again, evaluated at my point gives me negative 2. So then I've just plugged it into my formula. Z minus z naught equals f sub x times, it's really x minus negative 1, but that's going to turn into plus 1. And then minus 2 times y minus 2. And for tangent planes, it's fine to leave it like that, but oftentimes they'll just solve it for z. So in this case, they do distribute. We're not going to approximate anything with it. So if you solve it for z, we get negative 8x minus 2y. All right, one application problem I chose from our textbook. It's kind of an interesting one. This is a model for the surface area of a human body. How much surface area everybody has. Is a function of a person's weight and their height. Okay, and somebody has put together a model and figured out that the surface area in square feet is 0.1091 times your weight in pounds to the 0.425 times your height in inches raised to the 0.725 power. So let's say we find the linearization of this at a weight of 160 pounds and a height of 70 inches. Okay, so you're going to need your partial derivatives. F sub w, okay, all I'm doing is holding h constant, that stayed there. I'm bringing this down, okay, and then I'm subtracting 1 from the power. That's how I got the negative 0.575. You need a calculator for this one. This isn't a reasonable test question without a calculator. If you plug in 160 and 70, you get this small decimal. F sub h, similar. Keep w the same this time because that's constant multiplied by my variable. So I brought 0.725 down times this is this fraction, decimal, and then subtract 1 from your exponent. And when I evaluate that, I get 0.213. So my linear approximation, I needed the value, I needed f of 160, 70, and that's just plugging that into my function, gives me 20.5254. So my linearization formula, there's my general formula. And up here at the top, if you plug the numbers in, there's my linearization. So why do we want a linearization? Because we want to approximate something. Using this, let's see if we can approximate the surface area of a person weighing 162 pounds and a height of 73 inches. Okay. And also we're going to do for 170 and 80 inches. So the linearization, if you plug in 162 and 73, you get 22.255 square feet as your approximation. And what I did was I plugged 162 and 73 into the original function. I mean, you kind of need a calculator for both of them anyhow, and I got 21.271. So it's pretty close, right? That's what I mean. The approximation won't give you the exact answer, but it's usually pretty close. Unless, okay, now I computed it at 170 pounds and 80 inches tall, and I got an approximation of 28.114 square feet. If you actually plug it into your function, though, you get 23.201. Notice that's not so close. So the point, and this is worth noting here, when you do a linear approximation, you want to, we call the 160 and 70, where I derived my linearization formula from, is often called the center of my linearization. And what's going on here is when you do a linear approximation, if you're going to approximate something, you can't go too far from your center. Try to draw a picture here. Here's a mythical curved surface that might represent that function that we were talking about. Here's the tangent plane drawn at, in our case, 160 and 70 would be our x naught, y naught. If you move over 2 on the weight and 3 inches on the height, well, we can see there's going to be a small difference, and we saw that when we did the calculations. But when I did 170 and 80, I'm moving quite a far distance away from my center. And you can see what could happen is that your tangent plane is going horizontal where your surface might be curving away, so your error gets much larger. So that's just a good thing to know about linearizations. They only work well if you choose points that are close to your center. Okay.